Okay, this video is going to be a very short one. I would just like to go through one topic that I meant to cover. Sorry, when I looked at everything I had presented so far, it seems like there was one critical thing that I forgot to present. And this is going to be followed by another effort where I am going to try to show the superimposition of various molecules. Okay, so let's look first at the remaining topic, and this concerns syn and anti-additions to alkenes that are not cyclic. Cyclic alkenes, it's pretty easy to see that something's a syn or an anti-addition because there's only one way to present the ring, right? If we have a cyclopentane ring, we just draw a pentagon, and you can clearly see that something's on one side and something's on the other side, and that would reflect an anti-addition. But with a non-cyclic alkene, there are so many ways to project the molecule that it's really not obvious at all whether something's a syn or an anti-addition. So let's just look at one case here. So we're going to take this one compound here, which we'll call, this will be trans, and this will be cis. That's the only difference between these two compounds. One is cis, one is trans, okay? Alright, and I'm going to keep the same perspective in the drawing of the starting material and the product. I'm going to keep the carbon backbone, or the carbon skeleton, is going straight from left to right. Alright, so in the trans isomer, bromine is going to do an anti-addition, right? So we can get either compound A or compound B. Recognize that compound A and compound B have the opposite configuration at every single chiral center. Therefore, they're enantiomers. Okay? How do we make diastereomers of A and B? Well, we just change the starting material. We go from the trans starting material to the cis. And again, I'm going to keep the same perspective in the product and reactants. We're going to have the isopropyl group up and the ethyl group over to the side here. Okay, so adding bromine, it's going to add anti. One's going to go to one face here, one is going to go to the other. And we have compounds C and D. Recognize also that C and D have the opposite configuration at every single chiral center. Therefore, C and D are also enantiomers. Okay, now let's twist this around here. Let's draw this now from the same perspective that A and B are presented. Okay, so we're rotating C, and you get this structure immediately below C. Okay, and let's look at how A relates to C. Okay, so A has the same configuration at the left carbon, but the opposite configuration at the right carbon. This is how we define a diastereomer, right? Different at some, but not all of the chiral centers. So this is a classic example of diastereomers. Okay, its enantiomer is D, and I'm going to do the same twisty rotation on D here, and you see that we have the enantiomer. C and D are still enantiomers. They have the opposite configuration at every single chiral center. Okay, so what you see here is that each distinct stereoisomer of the alkene produces a distinct diastereomeric product. Okay, trans gives the AB pair of enantiomers, cis gives the CD pair of enantiomers. Okay, this is how we define something called a stereospecific reaction. Stereoisomeric starting materials give stereoisomeric products. Okay? In terminology, we're not going to go through this in this class, but we would call the A and B diastereomer the erythro, and the C and D diastereomer the trio. Okay, and this is a common feature. Toward the end of the class, we're going to talk about molecules that have many stereocenters, and you'll find that diastereomers tend to have the same name, and we just refer to the enantiomers as being either plus or minus, or by their R, S, or D, L configurations. Okay? Alright, so this is the more common situation where the alkene is not perfectly symmetrical. Let's see what changes if the alkene is perfectly symmetrical. In all honesty, all I've done here when constructing this diagram is I just took the previous diagram and erased a methyl group. Okay, so bromine here is going to add anti, and now we have A and B. Recognize now, I'm going to do one of these twist notations here for A and B. And look at this. This now has a perfect plane of symmetry here, right? Ethyl across from ethyl, bromine across from bromine, hydrogen across from hydrogen. Okay, I want to get rid of my name there. I don't want to identify myself. Sorry. And we can see the same thing in B. Turns out that A and B are not different compounds. They're not enantiomers. They're actually identical compounds. They are meso compounds. Okay, there should be a space here. Sorry. Okay, so A and B are good examples of meso compounds. All right, recall that when we have a meso compound, often we have another diastereomer that's not a meso compound, that's actually chiral, and we access that other diastereomer by just taking the other isomer of the starting material. So the cis isomer is reacting with bromine, and it gives C and D, and there's no plane of symmetry in C and D. If you turn it around, let me just draw something that looks like C from the same perspective. Okay, we'll keep this. Okay, sorry. This really doesn't work in Acrobat. Okay. Okay. But what you would have here is, if you did it with C, these two would have the opposite configuration, and you would not have a plane of symmetry anymore. Okay. Okay. Sorry, I cannot release the pen. What's wrong? Okay. All right. Sorry about that. Okay. So anyway, let's get rid of every marking here. Sorry about that. All right. So C and D are a pair of enantiomers, and they're a diastereomer relative to A or B, but remember, A and B really technically are not different compounds. Okay. All right. So recall a few weeks ago that we were looking at alkene additions. When we looked at a syn addition, which is the epoxide formation, we saw the opposite trend, where we got the meso from the cis isomer. Okay, and that's what you see here, is that an anti-addition requires the trans isomer to produce a meso compound, whereas a syn addition requires the cis isomer to produce a meso compound. Okay, so this is the last thing that I regret leaving it out of the previous videos, so sorry about that. And the rest of this, we're just going to look at attempts to superimpose things, okay? And I'm going to go to a different program called Chem3D here. All right. So let's imagine that if you look at these two compounds, and I'm going to move the pen here. I'm just going to have my hand here. I can't really write anything in this program. It's not designed to do that. All right, so my hand, the hand symbol is going up and down to show what I tell you here is the imaginary mirror. Okay, so let's take it for granted here that these two molecules are mirror images. If you want to know what they are, it's one chloro, one fluoroethane. Okay. All right. So I was just trying to illustrate this with the simplest chiral molecule. The carbon that I'm pointing to here and the carbon that I'm pointing to here are perfect mirror images of each other. This carbon has 4 different things attached to it. This carbon has 4 different things attached to it. No matter what I do, no matter how I rotate this, I can't superimpose it. Hydrogen and fluorine are kind of the opposite. Or let's see, let's try and line it up from the same perspective. Nothing's really lined up here, is it? Okay, just ethyl. Ethyl's lined up, but they're different. Okay, so let's line hydrogen up. All right, so hydrogen is basically from the same perspective in both molecules here. But you can see that chlorine and fluorine are messed up. Let's put fluorine in the same perspective, okay? All right, so fluorine and methyl fluorine and this carbon are kind of lined up in essentially the same orientation. But here you see that hydrogen and chlorine are lined up kind of they're on opposite atoms if you look at this superimposed structure here. So we can't superimpose mirror images when we have 4 different things attached to carbon. Let's look at another situation. Let's make 2 of these substituents identical. Okay, so here's actually now also a mirror image. Okay, here's the mirror image here. Here's the mirror. These molecules, they're not perfectly lined up, but you can sort of see they're approximate mirror images. Now these 2 carbons don't have 4 different things attached. They've only got 3 different things attached. So we ought to find some way where we can superimpose them, right? And let's see if we can do that. Okay, not yet. You're going to find that I don't do this operation perfectly. There's a little bit of a clumsiness in the rotation process, but I'm going to find some way to show you that these things do basically superimpose. Okay, so fluorine is kind of out. All right. And if we look at this, you can sort of see that they're starting to line up perfectly, right? Chlorine, or that's fluorine, carbon, and chlorine are kind of in the same perspective here that they are over here. Okay, let me see if I just have a hard time with these rotations here, getting everything exactly perfectly lined up. Oh, this is so good. Okay, this one's very close. Okay, so now you can see I was able to take 2 compounds that started out as mirror images and perfectly superimpose them. Okay, and that's the case when a molecule is not chiral. All right, we also said they had a plane of symmetry. Let's find that plane of symmetry. All right, I'm going to try to rotate this so that fluorine is perfectly in front of chlorine. Okay. All right, here we go. Here it is, over here. Right here. Okay, watch where the hand goes. This is a perfect plane of symmetry right here. Okay. If I imagine that this plane is here, everything that crosses this plane is the same, an equal distance on the other side of the plane. Therefore, this qualifies here as a plane of symmetry. Because it has a plane of symmetry, it is no longer, it is not a chiral molecule. Okay, I'm going to try to now, let's rotate this one. Okay. Yeah, so there's a plane of symmetry. We can also rotate it in such a way that chlorine and fluorine, okay, if they're perfectly in the board, okay, so, well, this is not a good plane of symmetry there, okay, but here, again, you see it perfectly right here. Here is the plane of symmetry, okay. Let's go back and to the other one and line up one of these chiral ones and see what happens. Okay, so I'm going to try to line up fluorine and chlorine perfectly. All right, so what would have been a plane of symmetry in the other molecule obviously is not a plane of symmetry, because when we go across this plane we don't see a perfect reflection of itself, right? Here's our plane going across. Hydrogen encounters a methyl group. Okay, it doesn't encounter another hydrogen. Whereas over here, hydrogen encounters another hydrogen in exactly the same orientation it is over here. Okay, so that's how we define a plane of symmetry. In this last one, we're going to look at a meso compound and prove that we can superimpose. Okay, so here is a generic meso compound. I guess this is 1,2-difluoro, 1,2-dichloroethane, the simplest meso compound you could ever possibly imagine. Okay, and this is chlorine, fluorine, methyl, hydrogen. All right, my arrow as it goes around looks to be going clockwise, so this is R and this is S. Okay. All right, so if we take this chiral molecule and we look across the imaginary mirror here, okay, we see a reflection of itself. We see the opposite chiral center, opposite configuration at every chiral center in this orientation. However, look right here. Watch the hand move. Right here, going across here is a plane of symmetry. Goes maybe it's better illustrated on one of the diagrams that we had in the PowerPoint video. But okay, since there's a plane of symmetry and this molecule isn't chiral, even though it's chock full of chiral centers, I ought to be able to superimpose it. Let me try and do that. Okay. All right, I think I'm pretty close here to superimposing this thing. Okay. All right. Not yet. I've got fluorine all wrong here. Okay, can I do it this way? Yeah, I can do it this way. All right, all I have to do is just turn it. Oh, okay, nope, still we got a problem. All right, chlorine. All right, we'll get it. I want to get it in the same perspective here. Okay, so that we can sort of watch them, see if they are superimposing. All right, this is about as close as I can probably get it. But here, we see the hydrogen is basically in the same place. Let me just sort of put chlorine out here. Ooh, okay, this is coming pretty close. All right. Okay. All right, here we go. Here you can sort of see that these molecules here are pretty much going to superimpose on each other, right? Chlorine over here to the left with the fluorine coming out. Chlorine over to the left with the fluorine coming out, hydrogen going back, just like we have here. All right, same perspective here. Chlorine to the left with a fluorine coming out, chlorine to the left with a fluorine coming out, and a hydrogen going back, hydrogen going back. All right, so the meso compounds superimposed. All right, and that's exactly what we're expecting. All right.